Now let's talk about the touchless interfaces. The touchless interfaces allows the user to operate the system by making gestures, which involves like moving arms and hands to communicate. The gestures are captured by using camera recognitions, sensors, computer vision techniques. It can easily recognize people's arm and hand gestures in a room. You would also have noticed this feature in your mobile phone. Like when you want to take a selfie and then you just raise your palm and you show your hand, then it starts the timer, and then in 5 seconds it takes your selfie. So basically, in a room, the camera can easily identify the beauty face, the hand gestures, and moving arm. But the problem or the challenge here is gestures needs to be presented sequentially. Now, if you see the research concern could be, to handle this, because gestures, if you move your arm very fast or hand very fast, then the camera cannot, capture that, because the gestures made by the user should be presented in a sequential manner in order to get understood and processed. Like, for example, when I talk with you, I have to put my words in a proper sequence, and then there should be a gap between one word and another word. If I jumble up the words, it cannot make a meaningful sentence. However, the words of the sentence could remain still the same, but will not make sense. Similarly, the gestures has to be presented sequentially in order to be processed. Uh, the modern cars, they have this gesture recognition system built in their dashboards. For example, like BMW iDrive enables the driver to control certain functions with the movement of hand. For example, if the user wants to slow down the volume, then he can show the hand like this, or mute to stop, unmute, and then back. So they are different gestures that are actually interpreted, and they are like pre-compiled. The user makes a use of those gestures similar, accordingly. That particular operation is carried out in the BMW iDrive cars. It uses a 3D camera, which is sometime, mounted over the roof lining of the car, or you have it like, for example, might be in this place, the camera could be there. So we talk about this to ensure they are safe gestures. Okay, to make sure that the gestures convey the gestures are conveyed in a proper way, and also the gestures are processed by the system in a proper way. They are developed and tested many times in something called as simulators. Simulators are not the actual system, but they simulate the system. Like, for example, you do not have a real car when you are testing it. You have it in a simulator, like, feel like a car, but it is stationary, doesn't move. So it is, tested in a safe environment. The research and the design consideration includes that the delineation of the gestures and how to recognize them. The term delineates the user gestures is very important to understand. In particular, what happens, like, for example, whenever the user is making a gesture, it is very important for the system to understand the starting point of the gesture, the movements over it, and the ending point of it. And we already discussed that the gestures have to be presented sequentially, otherwise they will not be understood. However, if the user makes a gesture, okay, deliberately, if he wants to do it for doing some purpose, then the gesture have to make the movement in a meaningful way so that the system understands it. So how, for example, when we are talking, there could be some words like, I'm saying and like write this. Okay, so when I talk, and there is a gap between the words, you can understand, right? You can understand that it doesn't. This distance doesn't mean the gap between the words doesn't mean anything. Similarly, when the user is making the gesture, it is like it is something like the user is trying to talk with the hands or with the movement of arm or with the movement of his body. So there could be now two things. He is like trying to move the hands in certain way to convey the message. Okay, so this makes the sense to the system. However, if the user is just waving the hand without any meaning, without trying to convey anything, it's just like trying to explain, or just like he want to move his hand to feel better, for example. So in that case, it becomes challenging for the system to understand and find out when it is simply waving or when it is making some important information communicate by the movement of hand. So this is the challenge. This is the challenge, the research challenge that still exists to find out the starting point and the ending point of the gesture. Okay, and to find that what is the waving without conveying any message, or what is the difference between dietic and the hand waving. Now the second research consideration is how realistic must the mirrored graphical representation of the user be in order for them to be believable. So as we have seen in the previous slide, that the user is trying to make the control the audio system here. So he is trying to for example, if he wants to mute the audio track which is running here, so he's just putting the hand like he's showing the stop sign from his hand. This is mirrored actually, right? So how realistic must be the mirrored graphical representation should be in order to in order for them to be believable. So for example, like he's making the hand like this, so the mirror image is the stop. So how this must be realistic, how it should be so realistic that when he is showing the hand in the display of the device, it should show the same sign. So how is that, how does that again imply to stop the audio from running in the media player of the car dashboard, for example? So it's like more of the thinking mapped to the realistic thing. For example, the user thinks to stop the audio file by showing the palm. Okay, so how realistic is that to carry out, by processing the gestures? The next very new type of interfaces used these days include haptic interfaces. The haptic interface provides a tactile feedback. What do we mean by tactile? It's like by applying vibration and forces to the person's body by using some actuators that are embedded in their clothing or a device they are carrying, such as a smartphone. For example, it's like this is the hand, and you see the sensors here. This is actually the device that is mounted on the finger, and inside this device there are actuators which will vibrate, okay, to give some kind of a feedback to the user. For example, like one of my colleague, she had completed her PhD in creating a haptic interface for car drivers, long drive drivers, for example, like truck drivers or heavy vehicle drivers, because they drive, at the time of night, because in the busy day, they don't get the permission to drive heavy vehicles, very big trailers, for example. for the safety of people, they are not allowed to drive in the daytime. So they drive in the night and often they fall asleep. So the haptic belt is tied on their tummy. So it will, it has some sleep sensors which will identify that the user or the driver is feeling drowsy, and then it somehow finds out that the driver is feeling sleepy and he's about to sleep. So at that time, the belt vibrates to just make him awake. Okay, so this is called as an haptic feedback. They provide the tactile feedback, which consists of vibrations or sense of touch or touch in the mid-air. Okay, so these type of things are created. For example, if you are trying to wave, try to shake hand with a robot. Okay, so when you shake hand with your friend, you see there is some warmth in her hand. From with whom you are shaking your hand, you feel there is a sense, right? So when you shake hand with the robot, if the robot vibrates, it gives you a feeling of touch. So such types of things are created by haptic interfaces. It provides a tactile feedback by applying the vibrations. Okay, and these vibrations are coming from the actuators which are embedded in their clothing or in their device. Okay, and this device could even be a wearable watch. For example, if you want to sleep and wake up by using an alarm, and you don't and your roommate doesn't like this sound of alarm, so what you can do is you can wear your smartwatch, have the alarm by using a vibration. So it will vibrate and it is on your hand, so it is on your wrist. You can feel the vibration and you can wake up, right? So such type of feedbacks are called as haptic feedbacks, and their interfaces are called as in haptic interface. So in this point of time, with that alarm example what I shared just now, the haptic interface is nothing but the app inside your wearable device which is trying to wake you up in the night. There are different types of feedbacks that are actually created with the haptic interface. The first one is the tactile. The second one is the vibrotactile feedback. The vibrotactile feedback is used to create a sense of touch between remote people. For example, you're sitting here and you have, your mother and the other end of the world, right? You people are remote. Now, if you want, to create a sense of touch, then we use vibrotactile feedback. It is very interesting and a very a new type of the feedback which creates a sense of touch between remote people who want to communicate with each other when they are not in the same place. The third type of feedback is called as ultra haptics, which creates the illusion of touch in the mid-air. Like, for example, your hand is in the middle of the air, and then you want to feel that something is touching. So, it is created by using ultrasound to make the illusion of 3D shapes. So, this is called as ultra haptic mid-air touch with ultrasound. So let's go to the next slide. Real time. Here is an example of a real time vibrotactile feedback. The lady here in the picture, if you see, there are so many sensors like a belt, and we have so many sensors here, and she's trying to play the violin. If she plays the violin incorrectly, the this haptic system or this interface creates a nudge. A nudge is nothing but a small push or a vibration, again, are short vibrations on arm, okay, on the arm and on the hand, just saying that it is wrong. Okay, for example, if she's playing it incorrectly, then it is sensed by the sensors mounted on her body. Okay, which vibrates and sends a signal to the arm or the hand. As I told you, like my friend, one of my colleagues, she created a belt like this, which was used to mount on the tummy of the drivers while they are driving. And then if they feel drowsy, the sensors senses that the driver is not driving the car properly, and then it creates a nudge or it creates a vibration and sends the feedback to the driver. Another very interesting example is like creating an artificial muscles, artificial muscles of e- exoskeleton with using bubble haptic feedback. Now, what is this bubble haptic feedback? The artificial muscles of the exoskeleton could be equipped with the sensors. You would have different types of sensors here, and this is, an actually an artificial leg kind of a thing with the sensors to detect muscle contractions and the movements. Like, for example, when you walk, the muscles in your thighs, they contract and they expand, and this is how the movements are done, right? So these sensors could then trigger specific feedback patterns in the form of bubbles, enhancing the user's awareness for the surroundings for providing feedback actions. The concept of the artificial muscle and a bubble feedback is used in various applications, especially in the field of robotics, healthcare, and virtual reality. So, this is about the skeleton. Now, the muscle could be designed to enhance human strength, the endurance, mobility by using artificial muscles. This could be pneumatic, hydraulic, or synthetic muscle fiber that actually does the job like a natural muscle. So, actually, this is not an actual muscle, it is an artificial muscle, which is creating the sense, the strength, okay, and the sensations by using the bubble feedback. Now, bubble haptic feedback involves creating tactile sensations like vibrations through the use of air and fluid filled bubbles. This technology can provide a more realistic experience by using various textures or forces against the user skin. It can be extremely helpful when the user is in the rehabilitation, when the patient is in the rehabilitation, to help the patient get the muscle strength in the affected limb as soon as possible. The research and the design consideration includes to decide where to place the actuator on the body. For example, we just saw that the actuators are inside the device, and device is mounted on the body of the user. In this case, it is mounted on the fingers. So placing this actuator on the device and placing or and mounting this device on which part of the body is uh, mm, uh, is a challenging question. So where best to place, where is it best to place the actuator on the body, whether to use a single or a sequence of touch vibrations, should be single vibration or sequence of vibrations, how to buzz and how to intense how to buzz and how to make the intensity of buzz more, how does the wearer feel. It is different contexts. For example, we might have one vibration to say something, two vibration to say something else, three vibrations to say something else. So how the user will learn the difference, like what the single nudge means, and so on. What kind of a new smartphone watch apps can use vibrotactile creatively? For example, slow tapping to feel like water drops. Like, for example, tapping is like for example, uh, like making a sound, right? So, Slow tapping can make or create a feel like water is dropping. Okay, meant to indicate that it is about to rain, and heavy tapping to indicate that it is a thunderstorm. Okay, so uh, tapping, creating vibrations, creating touch is like all are part of the haptic interfaces to create the to give the feedback to the user. Now we have another thing called as a multimodal interface, which provides enriched user experience by using different modalities such as touch, sometimes sight, sound, and speech. It supports flexible, efficient, and expressive means of HCI. Most common combination of these modalities include speech and vision. It can be combined with multiple sensors input to enable uh, the other aspects of the human body to be tracked. For example, if I gaze, looking at something for a longer time, facial expression and even a lip movement can also be imitated or taken care of. Provide inputs for customizing the user interfaces. Here is an example of tracking a person movement. In the multimodal interfaces, we talk about tracking uh, how the user is changing the faces. How, while talking, there is a lip movement, eye gaze. It can even track the eye gaze. Here is an example of a person tracking a person movement. For example, there is a man in the interface here, and then this man is, trying to trace. So you see, there is, the prototype of their action. A kinetic camera can detect multimodal input in real time using RGA cameras for facial recognition and gestures. Depth of the camera for movement tracking is used. Microphone for voice recognition is used. It is used to build model of person. This is the person. This is the model of the person, and represent it like an avatar. On display program, an avatar can display the movements as well by using a program behind it. The research challenges includes the need to recognize and analyze user behavior. The behavior could be speech, gesture, handwriting, or eye gaze even. It is much harder to calibrate these than single modality system. Sometimes in speech, the voice is required. In gestures, the movement, the start and the stop of the hand wave, for example, is required. Eye gaze is just like, capturing the sight. So it is difficult to calibrate all of them in the same time or in the combination when compared to the single modality. For example, in the gestures, we were, just taking care about the touchless interfaces. We're taking care only about the gestures, and we saw there are research, considerations with that. Now, in the multimodal, many type of challenges are surfaced because we are sometime using touch, sometime using touchless interface, sometime we are using voice interface, sometime we are using the different interfaces. So it becomes a bit complex. What is gained from combining different inputs and outputs is again, challenging. Is talking and gesturing uh, as human do with other humans a natural way of interacting with a computer same or not? And of course, it is not same. It's much simpler when we do it in the real time. But when we do it, when we talk or when we make the gestures and try to operate the device, it becomes really challenging. Shareable interfaces. Now, what are shareable interfaces? Shareable interfaces are designed for more than one person to use in the same time. So it provides a support to collect multiple inputs from people, located co-located groups. For example, they can also make the changes here, and she can also see the changes here. Large walls display where people use their own pens and their gestures. Interactive tabletops, like this is a tabletop where small group can interact with information using their fingertips. For example, Diamond Touch, Smart Table, and Surface are the examples of shareable interfaces. A smart and an interactive tabletop interfaces shown in this picture. Benefits: large interactional, it creates a large interactional space that can support flexible group working, can be used by multiple users, can point to and touch information being displayed. Simultaneously, many people can view the interactions and have the same shared point of reference as others. It can support more equitable participation compared with groups using single PC. The design considerations and the research consideration includes to decide the size, orientation, and shape of the display that can be good for collaboration. Horizontal surfaces are better than vertical surfaces while supporting turn taking and collaborations working in a co-located groups. Larger size tabletops does not improve group working, but it encourages more division of labor. Like if you have larger size of table, more people can, come and work on it in the same time. Having both personal and shared spaces will enable groups to work on their own and on their and in the group and as a group also. A design challenge is how to bridge across device applications and time such that the people interactions are seamless. So again, here bridging across devices is a big challenge. You could have, for example, we have seen here, this lady is, using a shared interface, and then these people are trying to provide their interfaces, to provide their contribution into the interfaces or participation into the interface by using gesture or pen. So the pen can come from a different company, the screen can come from a different company. So it's really difficult to have bridge across the devices and work seamlessly. The another type of interface includes the tangible interface. So now we just saw the shareable interface. Now we are talking about tangible interface. The tangible interface are something that enables the user to physically, they are trying to physically move it, physically interact with digital content. So basically, this is the digital content, and physically they are moving it, right? So this is called as a tangible interface. Tangible means something that can be touched. We do that by using sensor-based interactions with physical object, like for example, bricks are coupled with the digital representation. When a person manipulates, makes some changes here, the effect in the digital world could also occur in a form of an animation, for example. Digital effects can take place in number of media and places, or they can be embedded in a physical object itself. So this is a new type of interface. User receives the tactile feedback through a vibration from the physical object. This feedback can include sensations such as taste, touch, pressure, resistance, and providing more engaging in experience. So it's like a way of how you physically interact with the digital world. Examples include flow blocks, arc, and magic cubes. This is like a magic cube. Let's see what does it do. Magic cube connects physical electronic components and sensors to make digital events occur. For example, change of a color depending on how fast you shake the magic cube. Flow blocks depict changing numbers and lights embedded in the block. It may differ depending on how they are connected together. ARPs is like physical models of buildings moved around one tabletop. Is used in the combination with tokens of wind and shadows. Digital shadows surrounding them to change over time. So these are the examples. Benefits. It can be held in one or both hands. Okay, tangible interfaces can be held in one hand or in both hands. And combined in your and combined and manipulated in ways not possible using other interfaces. So the best thing about the tangible interface is that it can be touched. It can be held in a single hand, or it can be held in a double with a double hand. The beauty is that it is not possible to manipulate any kind of any kind of interaction with this interface seamlessly, and this is not possible with any other type of interface. So it is, because it is allowing you to touch and make changes physically into the digital world. Objects can be placed on the top of each other, beside or each other, or inside each other. It will allow one or more person to explore the interface at the same time, encourage different ways to representing and exploring a problem space. People are able to see and understand situations differently, can lead to greater understanding, and can facilitate creativity. So this is about the uh, chapter 7, part 3. Thanks for watching.